Okay, so we're going to start using WMS pretty soon. If you haven't already downloaded that and installed it, please do so within the next couple of days. It's going to be the basis of the projects that we do this semester, so it's a really important excuse me, software package. Homework 6 is on Blackboard right now. It's applying the NRCS approach to figuring out how much runoff there will be during a rainfall event. That's due on Monday. And what we're going to do today is talk about some methods that have been developed to generate a unit hydrograph when you don't have actual data for a specific watershed. Ways to synthesize unit hydrographs. So, does anybody have questions? Okay. You may remember that a unit hydrograph can be developed if you have a rain gauge in a watershed and if you have a stream gauge in a creek or in whatever water body is receiving the flow from the watershed. And when you have that physical measurement available, then what you would do is you'd look for some sort of a rainfall event that's pretty close to a unit of rainfall excess. And so what you'd need to know to do that is you'd have to be able to calculate the infiltration for the conditions that you've got in the watershed. You need to have some approximation for the initial abstractions. And so let's just say that there was, during a certain storm that you're monitoring, 1.2 inches of rainfall, and that your abstractions and infiltration are 0.2 inches, and so that gives you a storm depth of 1 inch. So if you had that, then you could use the physical measurement from the stream gauge to have an actual unit hydrograph. And the way that stream gauges typically work is it's just measuring the depth. It's what we want is to know the flow rate, the Q versus time, but there aren't ways to directly measure the flow rate. What we have to know is what is the depth of flow at any given time, and then we would use some sort of a survey of the stream to know what's the relationship between depth and flow rate. We'd apply another equation like Manning's equation to apply a depth versus cross-sectional area understanding to get a flow rate out of it. So there are a couple of steps there, but what we ultimately want to know is how much rain is going to cause how much runoff. But there are very few of these watersheds where we happen to have had a stream gauge and a rain gauge over a long enough period that we could generate an actual unit hydrograph. And so the SCS unit hydrograph method is a way to synthesize a unit hydrograph to have some sort of an extrapolation of what could occur, or maybe a better way to put it is, you'll never actually see the behavior that's predicted by a unit hydrograph, but it's still useful for planning. There was a general during World War II, Eisenhower, who said that plans are useless, but planning is essential. And so the same thing, I guess, maybe is true for unit hydrographs, where if you design your infrastructure to accommodate the storm that's predicted by the unit hydrograph, then your infrastructure will be sized appropriately. But will you actually ever see a storm that has the hydrograph shape of a unit hydrograph? No. It's never going to be exactly looking like what's predicted by the synthetic unit hydrograph. The time to peak could be different. The characteristics could vary in a lot of different ways. But we can still, hydrology is very much a science of good enough, where we don't know the exact answers, particularly because we're projecting events in the future, and we're projecting them based on probabilistic data. And the probabilistic data we're using for estimating the future is gathered at just a few locations over a really large area. So there's all sorts of statistical approximations and guesses, and somehow yet it's still mostly good enough. You don't hear about failures too often because there are safety factors and there are like best practice techniques that can avoid really costly failures. But What this is, if you look at the figure that's on the screen here, is it's a hydrograph shape. And so you can see that there's a dashed line that's a triangle, and the actual shape of the hydrograph somewhat approximates the shape of this triangle, where the first front side of the triangle has a length of 1 compared to the trailing leg, which has a length of 1.67. And so the first component of this unit hydrograph is the understanding that it usually takes longer for the water to decrease after a storm event is finished than it took for it to increase at the beginning of a storm. That the watershed is more likely to drain slowly after the event's over. So that's why the base of the hydrograph is kind of biased towards the right side, past what's defined as the time to peak. So this figure is showing a couple of different things. First of all, we talked about the curved shape, which is just a way of trying to approximate what could be seen over a wide range of average conditions. And this is in response to some unit of rainfall. So this gray shaded area here is representing the unit of rainfall excess that caused this runoff hydrograph. There's a width of the unit, so T sub R is how long that rainfall event was. And a pretty typical starting point would be 1 inch of rainfall, but it's not always 1 inch of rainfall. It could be a 1-day storm. I'm sorry, 1 hour of rainfall that the 1 inch of unit depth has fallen over. So the width of it represents a time. This other curve, the mass curve, is just showing the cumulative amount of water that's come out of the watershed over time. And it's useful to us if we're sizing a pond, like some sort of a detention pond that all of this water is going to be routed to, and we wanted to know at what time has a certain fraction of the water arrived at the pond. But it's less likely to be the key factor that we're interested in. More typically, we're interested in how long until this peak arrives from the beginning of the storm. So the time to peak, T sub P, we're interested in that. And we're also interested in how high the peak is. So what is the peak discharge? Now, by the way, if you look at the labels here on the vertical axis, this is showing lowercase q to q sub p. And so that's saying like the unit flow rate. So it would be how much flow rate is there per unit of watershed area. Or you could use the same shape to predict the overall flow rate at a given time relative to the peak flow rate. So if now you look at the numbers, it goes up to 1 because that represents 100% of the peak flow is at the time to peak. So on the horizontal here we have units of 1, 2, 3. So 1 represents how long it took from the beginning of the storm to the time of the peak. And then 1 on the vertical axis is the ratio of the flow rate at any given time to the peak flow rate that's observed at this time to peak. So we're going to use this to extrapolate to watersheds where we don't have actual measurements of rainfall runoff response. And so what I think of this as similar in concept to the Snyder's synthetic unit hydrograph. Because if you remember, the Snyder's synthetic unit hydrograph was applied based on shape factors and coefficients in situations where we didn't know the actual drainage conditions necessarily to the same level of precision that we'd need to measure it physically, how long it takes for the water to be flowing over the sheet, how long in shallow concentrated, and how long through the stream. But this is really easy to apply in computerized simulations of watersheds. And so we'll use this SCS unit hydrograph method a lot when we get into the watershed modeling using WMS, because it's a way to just say when the water is arriving at the outlet. It's a way to tell you the temporal distribution of the hydrograph, how long the flow is going to be coming out of the watershed. So a key parameter in this is the lag time. So the time to lag. So if you'll notice on this figure, what it's showing us is the lag time is from the midpoint of the storm to the time to peak. So that's defined as the lag time. And we have a formula that allows us to estimate the lag time based on the slope of the watershed in percent and the storage characteristics. And so remember, S from the NRCS method is related to the curve number. And so if you have a really low curve number, then you'd have a higher depth of storage capacity. If you've got a large curve number, then S would be lower. And then the last term in here, the length, the hydraulic length, is how far the water is flowing through the watershed to get to the outlet. So it's the maximum distance, the furthest point away, hydraulically speaking, the travel time. So this is just it's not a fundamental equation. You can see this 1900 and then the L to the 8/10 power, this storage term to the 0.7 power. It's just based on lots of observations, and so there's some inherent inaccuracy and imprecision in that, but it's still useful for planning purposes, and it can give us a good starting point to understand the range of possibilities. We can calculate the time to base. So T sub B is the overall duration if this is going to be represented as just triangular from the start of the storm until the end of the triangle. But the way that the data that I'll show you in a minute, and I've also loaded on Blackboard the table of values, because we're going to go through an example using Excel and actually generate a hydrograph for a hypothetical scenario here in Huntington. It starts tapering down really slowly at the end, and that doesn't have the same kind of triangular characteristics as this first part of the hydrograph. The time of concentration is 5/3 the lag time, and so when we're using WMS, sometimes we'll need to calculate the time of concentration from the lag time. There will be other cases where we need to calculate the lag time from time of concentration, if that's what we know. And so to do that, the lag time is just 3/5 of the time of concentration. So it's really easy to switch between the two. I'll point out that the curve numbers and the formulas that we use to calculate S from the curve numbers has to be in units of inches. So curve numbers are meant to be used in the US customary unit system. Okay, so this is going to tell us the temporal distribution of the flow, but we still have the question is, what is the flow rate? How much water? What's the peak that it's going to reach? Because this shape tells us at any given time, the fraction of flow compared to the peak, but how high is the peak? That's what this next formula answers. How high is the peak? So if you know the watershed area in square miles, we can use this formula to find out the peak discharge for a unit of rainfall excess. And so there are these peaking factors, and that the typical watershed, just kind of standard value, would have a coefficient of 484. If we have an urban area that's steep topography, then the peaking factor is higher. If you've got rural areas where water moves more slowly and where there's going to be enhanced infiltration effects, then the peaking factors are lower. So the 484 that's listed here is just right now for typical SCS, but you could adjust that coefficient based on your understanding of the watershed that you're applying this to. The Q here, the amount of direct runoff, if we're generating a unit hydrograph, then we'd use 1 inch of runoff depth. But if we have a storm of of greater depth than generates the unit, then we could substitute in a different value. So this is a little bit confusing for some people who normally, when you think of Q from hydraulics, you're probably accustomed to thinking in terms of volume per time for the units. You know, for example, cubic meters per second. That's what we usually use as units of Q. Here, the Q just means depth. But then this lowercase q that comes out of the formula is going to be cubic feet per second for whatever depth you've put in terms of Q on the right side of the equation. Okay. So we're going to use the scenario here of a 3 square mile watershed that has a curve number of 86. And so that's on the high side. We're going to assume, for example, that this is in Huntington, that this is a mostly urban watershed, that the soil values are tending towards clay, that there's a lot of impervious area. Whatever the case may be, we've done the weighted curve number calculations, and it's 86 for this 3 square mile watershed. Let's find out, first of all, if we had 1 unit of excess rainfall. So for this first part, we're going to say Q, this big Q, is 1 inch. Then let's find out what is the time of concentration, the time to peak, and the unit peak discharge. And then with that defined, what we can do is apply it to the storm depth that's associated with a 2-year, 24-hour storm. And then we'll go to this table, which I put onto Blackboard, to create an actual graph of the hydrograph. So the first steps that I'm going to pause so you can calculate is calculate using the formulas that are provided here. First of all, you'll need to calculate S. So the equation for that's down here below. So use the curve number to calculate S. The hydraulic length, by the way, in this formula should be in feet. So you're going to have to convert the hydraulic length that's given in the example of 1.2 miles. L has units of feet. So does anybody remember how many feet there are in a mile? 5280 feet per mile. Okay, so I've given you the length in miles, convert it to feet, and then the slope of 3%, you just put that in directly as the number 3. You don't put in 0.03 for y. So y has units of percent as whole number. So not rounded off as a decimal is what I mean. All right. So let me stop talking, give you a chance to do these calculations, and then we're going to get into Excel after a bit. So here in the problem statement it says the unit hydrograph, then let's let Q, the amount of rainfall excess, be 1 inch. In this last part of the example where we applied the 2-year, 24-hour storm, then we'll actually go and look up the actual rainfall depth and be able to scale it accordingly. So here on the whiteboard I've written that the storage is 1.63 inches because of the curve number of 86. The lag time is 0.656 hours. Time of concentration 1.093 hours, and therefore the time to peak 0.729. So that is telling us that from the start of the storm up to this peak is 0.729 hours. And how high is the peak getting? Well, for every inch of rainfall excess, then we're going to see the Q sub P was 1,992 CFS per inch of rainfall excess because we put 1 inch into Q. So if you know the storm depth is something other than 1 inch of rainfall excess, then you could put the actual amount into that, or you could just use this value and scale it when you start on the Excel portion, which is what we're going to be doing next. So any questions so far for parts 1, 2, and 3? All right. Well, let's find out what is the actual 2-year, 24-hour storm depth so that we can apply the hydrograph. And so go to the precipitation frequency data server. And we're going to want to know the depth, not the intensity, so we'll leave it on the default there. And we can just type in Huntington and it'll find it. All right. So it was saying that we want to be able to know what does the hydrograph look like for the 2-year, 24-hour storm. So here's 2-year, the 2 column, down to 24-hour, 2.64 inches of precipitation. So the 2-year, 24-hour precipitation depth is 2.64 inches. Okay. So of that, how much precipitation excess will there be? Because remember that this hydrograph that we've just generated, it's based on rainfall excess. Q is rainfall excess. It's not the precipitation amount. It's not the rainfall amount. So the next thing that we have to do is we already have calculated S. Let's put that into the NRCS method and find out for this 2-year storm, how much of the 2.64 inches is excess. Okay, so you'll remember that the NRCS method says that the precipitation excess, P sub E, is the precipitation minus 0.2 S, and then that squared divided by P plus 0.8 S. Okay, so our precipitation is 2.64 inches, and then multiply that minus 0.2 times 1.63 inches, which was our storage depth that we'd calculated. And everything in the numerator is squared, divided by 2.64 inches plus 0.8 times the storage of 1.63 inches. Okay, so can somebody, or all of you with your calculators, tell me how much precipitation excess are we going to have of the 2.64 inches? How much will be flowing over the surface because it didn't infiltrate, because it's not a part of satisfying the initial abstractions? So there was 2.64 inches of precipitation. The NRCS method says that of that 2.64 inches of precipitation depth, there is a rainfall excess depth, also called the runoff depth, is 1.36 inches. So that's approximately half of the 2-year storm will be contributing to runoff. So now what we want to do is actually generate a hydrograph, and we're going to use this data to do it. So if you've got your computer, go to Blackboard and download the Excel file that I've loaded into the course page. I think it should be at the bottom. This example SCS unit hydrograph file. Download that. So we've got time ratio, discharge ratio, and up here at the top, let's add a couple of rows because there are a few like constants that we want to have some room for at the top before we get into calculating the hydrograph itself. So right click and insert 2 rows so that we can have the time to peak in hours, which we calculated that on the whiteboard. It was 0.729. And then we'll want to know Q sub P, which was, the units of that was CFS per inch of precipitation excess. And we found that was 1992 CFS per inch of rainfall excess. And then the actual precipitation that we saw for this storm, the storm in question, the 2-year, 24-hour storm, had a depth of 2.64, but of that 2.64, the precipitation excess depth is only 1.36. So if I just kind of refresh what these things are, this is the precipitation excess depth calculated by the NRCS method. Okay, this Q sub P calculated by the SCS method, and this is also part of the SCS method. All right, so we're going to want to generate a hydrograph that has time in hours and discharge in terms of CFS. And this is going to be pretty easy because all we're going to have to do is the time will be this time ratio multiplied by the time to peak that we've got up at the top. And so we're going to want to anchor that reference, and so it's multiplied by the time to the peak, and then you can press F4 or put the dollar signs in manually. But if you look under time ratio, it says time relative to time to peak. So time divided by time to peak, so that we know that the time to peak has actual units of hours, whereas this ratio is unitless. So if we multiply a unitless ratio by the time to peak, then we're going to have at each row the time in hours to get to that point. So we'll be back down to a flow rate of 0 after 5 times the time to peak, which is 3.645 hours. So this is turning the abstract into the real. Although remember that the real is just kind of an extrapolation, a prediction, an approximation. We wouldn't actually ever see exactly the behavior that's going to be predicted with this. We just use it for planning. All right, what about discharge? Same idea. So we have to multiply the discharge ratio by the precipitation excess amount. No, that's not what we do. We multiply it by both the Q sub P and the P sub E. Yeah, because this Q sub P tells us what it would be for 1 inch of rainfall excess, but we have more than 1 inch of rainfall excess. We've got 1.36. Okay, so we multiply the ratio by this Q sub P, and if we left it at that, then it would tell us the discharge based on 1 inch of precipitation excess. But we have 1.36 inches of precipitation excess. So I need to anchor both of those references up at the top. Those are constants. I don't want the spreadsheet looking elsewhere as I drag the cells down. But does everybody understand why we're multiplying it by both of those things up at the top? By this first one converts it from rainfall excess depth to flow rate, and then the second one converts it to how much rainfall excess did we actually have, whereas the original unit hydrograph is based on just 1 unit of rainfall excess, meaning 1 inch. So if you carry that through, then what we should see is that here at the 1, the time to peak, the highest flow rate that we're going to see is 1.36 times the 1992, which was the peak. So let's just double check that. Let's see, 1992 times 1.36, yep, 2709. Okay, so now we've got time versus discharge. And just to see if that follows the shape that we would expect to see, let's insert a figure. So insert, and we want to do a chart that is smooth without showing the underlying data points. And so this scatter with smooth lines. Okay, so we'll create that, and then I have to select the data for it. So up on the ribbon here where it says select data, we're going to add a series, and for the X values it's going to be the time in hours. So I'll click at the top, and then I'll just do Shift, Control, and the down arrow button, and it'll select through the entirety of the data. Enter. And then for the Y values, it's going to be this adjacent range of cells, and so Control, Shift, up arrow, but I don't want to include the label, just the values themselves. So if you look at what's included, it's the time on the X-axis, the discharge on the Y-axis. Okay. We need to put a title and units and labels and stuff in there. So when I click OK, then here at the right, I'm going to insert an axis title. And so on the horizontal axis, we'll call that time in hours. In the vertical axis, this will be discharge in terms of cubic feet per second. And then the title I'll call Huntington Watershed 3 miles square CN 86 2-year storm. So 2-year return period, 24-hour duration. This is what the watershed's going to look like, the hydrograph coming out of the watershed. These lines don't do anything for me. I'll delete them. All right. That's a pretty high flow rate. You know, 2,700 CFS, that's a lot of water. But that's also a very high curve number. 86 is, I mean, that would be mostly complete urbanization. So this would be for a watershed that doesn't have any kind of detention ponds. It doesn't have any stormwater management features. This is just kind of urban development run amok without any mitigation to try and reduce how quickly the peak arrives, or to reduce how much runoff there is from a storm. Any questions? Anybody need to see a certain part again? So remember, a big part of this course is conceptual. It's not just putting numbers into a formula. It's not just clicking on the computer in a certain place. It's being able to understand and explain why we're doing certain things and how the concepts fit together. And so the thing I'd like you to take away, the most durable thing from what we've talked about today, is what the purpose of the SCS unit hydrograph is for. Its purpose is to give some sort of a temporal distribution of the flow rate, where the NRCS method is just about depth. You know, the NRCS method will tell you for a certain amount of precipitation, how much precipitation excess is there. And that's good to know. That's useful stuff. But we need to know when it's going to arrive and the flow rate in cubic feet per second. So just knowing the overall depth of rainfall excess doesn't give us all the details we need to size pipes, to size culverts, to make sure that bridges are high enough off of a stream. All of those things demand some sort of a temporal distribution of when the peak is arriving and what the actual flow rate is in terms of cubic feet per second or cubic meters per second. And so this SCS method is a very simple, easy to apply approach to generate that information. So that's all I have for you today. Remember that what you've got right now is the NRCS method assignment, which is due on Monday. I think I've fallen behind on grading your assignments. I don't have a grader, so I'm doing it all myself. I'm going to need a weekend before I catch up, so I'll try and get those grades into the grade book as soon as possible. Remember that WMS should be installed, and we'll probably have a quiz. I don't exactly know when, but you know, it feels like a quiz is in the air. So, can you feel it too? Yeah, I feel it. So, we'll have a quiz sometime, probably in the next week.